All right. So we are in section 5.2, okay? 5.2 is something called the definite integral. And so let's start by looking at what we know and versus what's new. So what do we know? Well, so far we know antiderivatives. And in particular, we know that if we have like the antiderivative of x dx. Anybody remember where that came from? Like, what was the function that we took a derivative of to get x? Yeah, and let's just change all those minuses to a plus. And so we're going to get x to the 1 plus 1 over 1 plus 1. And then there's one important thing that I said we better not forget. We're going to have a plus c at the end. And that c only needs to be capital for WebAssign. Otherwise, a lowercase c is absolutely fine. Okay. And so if we clean this up, we'll get x squared over 2 plus c. And so that is one of the rules that we learned about taking antiderivatives. But another word for antiderivatives, so when we see something that looks like this, another word for that is we sometimes call it the indefinite integral. Okay, so you might hear someone say, hey, find the antiderivative. But more likely than not, you will hear someone say, find the indefinite integral. Okay, those two words mean the same thing. Now, we've also talked about approximating area. And in particular, we've looked at a lot of rectangles, and we have sort of an LRAM, that left approximation. We have a right approximation, and we have a mid approximation. Okay. And on this week's quiz, you will have one more opportunity to practice that idea of rectangular approximation and how to draw those, okay? But one important thing to note here is that for each one of these, all the rectangles had the same width. Whoop. Okay, meaning that we divided the sections into equal sized widths, and it was only the height of the rectangles that was changing. Okay. And one more important idea about that approximating area, we knew that the rectangles, like if we had more rectangles, we would actually get a very accurate area. Whereas if we had fewer rectangles, maybe the area we get would be less accurate. Okay, so a few things to consider here. Consider how accuracy comes into play for your answer, and also the idea of over versus under estimates. Okay. And so that's what we covered last week. All right, we stopped talking about slope and we started talking about the area underneath the curve. And so what's new for today? Well, what's new for today is that we're going to take a look at something called a definite integral. Now that is only missing 2 letters from our indefinite integral, but we want to know what is a definite integral. Okay. We also want to know how it connects to the idea of area. And then we're going to take a look at something called net area and total area. And we are also going to look at properties of definite integrals. And finally, we're going to take it look at something called the average value theorem. All right. Now I want to make a note under this that this is not the same as that sound is delightful, huh? Not the same as the mean value theorem. All right, so let's now talk louder so we can talk over the leaf blower in the background. All right, so we're going to take a look at oh, okay, perfect, thanks. Thank you for that. Okay, so we're going to take a look at evaluating definite integrals with geometry and the idea of antiderivatives, okay? So we're going to start off with this problem here, which is given the function 2x plus 3, and we're taking the integral from 2 to 4 dx. What does that even mean? Okay, and so here's what this means. We have some function 2x plus 3, and that function is graphed below. Okay, so this red line is the function 2x plus 3. Now, I'm wondering if you can tell me, like, let's say I didn't provide a graph, how would you graph 2x plus 3? All right, so not a trick question. How do we graph 2x plus 3? It's a positive slope line. Do we happen to know the y-intercept here? Y-intercept is 3, and that slope is going to be 2. So we know b equals 3, m equals 2. So we go ahead and we plot that line. Okay. Now let's worry about the integral part. Okay. So if we kind of zoom into this notation over here, we're going to notice that there is a number on the bottom. Okay. And let's go with green for that. There's a number on the bottom, 2. And there's a number on the top, 4. Okay. Now the 2 and 4 tell us x values. And in particular, they tell us where to start looking for our area, and the top number tells us where to stop looking for area. So I'm going to go ahead and go to x equals 2, and I'm going to draw a line from the function, whoops, to the x-axis. Yeah. So that green highlighted 2 represents this green vertical line here. And then I'm going to do the same thing for 4. So I'm going to go to 4. I'm going to draw that line. Okay. So I've got a green line and a blue line. And now the integral symbol. Okay. So that squiggly symbol and the dx. Okay. Here's what that tells us. That tells us for the graph, we want to find the area between that graph and the x-axis. So all of this area. Okay. So let me pause for a moment and make sure that makes sense where we got all the different parts from. Are we all okay with the picture and the equation that we have above matching? You can give me a quick thumbs up or just type yes in the chat. Okay. All right, good, good, good. Okay, so what shape did we just shade in here? Ah, yes. So our shape is a trapezoid. Okay. Well, if I want to find the area of this trapezoid, I best know the area of a trapezoid formula. Anybody happen to know that area of a trapezoid formula? There are different ways to write it, but some people do like a base 1 plus base 2 times the height all over 2. All right. So let's plug in our numbers. Okay. So area, actually, let's write it using the fancy notation. So the integral from 2 to 4 of the function 2x plus 3, do not forget the dx, equals. Now let's apply the area formula. So we need to know base 1 plus base 2. We need to know the height, and we're going to divide that by 2. So looking at the diagram, what might we say is base 1? Like, which of those 4 sides is it? Is it the red line, the blue line, the green line, or the x-axis? Ah, okay. So it is, in fact, not the x-axis, okay? And I know that's weird, all right? So here's the deal. When we draw a trapezoid, okay? So if I just draw a trapezoid up here, this is normally how we draw them, right? But the things that make it a trapezoid are not just that it has 4 sides, but specifically 2 of the sides are parallel. And it's the parallel sides that are the bases. It doesn't matter if you call this one base 1 or base 2, but the other one will just be the other one. And then our height, and this is like a throwback to middle school or high school geometry, that height needs to be perpendicular to the bases. Okay. Now, I feel like we all draw trapezoids this way, right? But what we need to be careful of is, does it meet our definition? As in, the bases are the parallel ones, right? So if we considered the base as the x-axis, I'm pretty sure that's not parallel to the other line, right? So we can't call the x-axis the base. However, we can, as Graham pointed out, maybe we call this one base 1, and that sure is parallel to the other base. Okay. And so Graham said that the green line was base 1. And he said that that line had a length of 7. Do we agree with that? Yeah, because that's the y value there, right? That green line we drew is 7 units long. Okay, what about base 2? We'll squeeze that in right here. How big is base 2, or what is the length of base 2? Yeah, I think we're going to go with 11. Okay, so we've got base 1 is 7, base 2 is 11. And someone tell me what the height is here. And the height is 2. Good job, good job. All right, great job. Everyone contributing ideas to this. So For our base 1, we're going to go ahead and put in 7 plus our base 2, we're going to put in 11. The height is 2, and we have 2 down here. I'm going to go ahead and reduce, and then we'll get 7 plus 11 gives us 18 as the area. Okay. So using what we know about area, we were able to figure out the area of this shape, right? Not too hard. We just need to remember the trapezoid formula. All right. But let's go back to this equation and say, well, what if we didn't have a diagram? Okay. What if we did not have a diagram? So let's take the equation, the integral from 2 to 4 of 2x plus 3 dx. Okay. And what we're going to do is, you don't need to do this part, but for some of us, it might be helpful. 2x to the first power plus 3x to the 0 power dx. Okay. So all I've done is sort of rewrite it so that I can see the powers, because just like folks did earlier, we're going to go ahead and find the antiderivative by using the power rule. That's sort of like our one rule that we know so far, okay? And so if we take the antiderivative of the first part, okay, so this part, then we'll have 2 times, let's see, x to the 1 plus 1 over 1 plus 1, all right, plus, so this part corresponds to that orange part, and this part plus 3 x to the 0 plus 1 over 0 plus 1. And I'm going to do something right now that might seem in contrast to what I told you before. I'm not going to write a plus c. Okay. And there's one more thing I'm going to do before I move on to the next line. And I'm going to write this part in blue just so that we can see it better. Okay. I'm going to put brackets around the whole thing. Okay. And then I'm going to draw a little line at the bottom right corner of this last bracket. And at the top of this line, I'm going to put the top number from my antiderivative, which is 4. And in the bottom, I'm going to put the bottom number there, which is 2. So I think we had said that there was this green number, which is this green number, and then a blue number, which is, oh no, this blue number, this blue number, okay? So let me pause for a moment. How are we doing? We doing okay? So this power rule that we learned last time, all right, is something that if it doesn't seem really easy for you to do, I would go find a resource with lots of practice problems on the power rule, and I would do a bunch of those just to kind of get the hang of it, okay? But the only new layer we've added is, instead of a plus c, we sort of have these two numbers hanging out, okay? And so what we're going to do now is we're going to take the top number, 4, and we're going to plug it in to here. And then we're going to take the bottom number 2 and plug it into here. All right. But before we plug in some numbers, maybe let's clean this up a little bit so it doesn't look as intimidating. So what do I have? 2 times x squared over 2 plus 3x, I think is what that becomes. And again, I have 4 and 2. And let's simplify this just a little bit more. I think I can clean this up to be x squared plus 3x, and then 4 and 2. All right. So if the first part was scary for you, like that second line, maybe as soon as we cleaned up some of those numbers, hopefully that helped take that anxiety down a little bit, okay? So now let's plug in the top number, let's plug in the bottom number, and we are going to subtract them, okay? So 4 squared plus 3 times 4 minus 2 squared plus 3 times 2, 4 and 4, 2 and 2, just to keep track of where those numbers came from. All right. And then we're just going to crunch some numbers. 16 plus 12 minus 4 minus 6. Let's see, that gives us 10 plus 8 should give us 18. Okay. So let's zoom back out for a moment. And that's weird. There we go. And holy cow, our answers from both the geometry and the antiderivatives were the same. Okay. Now, this work on the right-hand side, the only thing that was different between this problem and the ones we did last week are that now we have numbers with our integral symbol. Okay. And so if we think about the word definite integral, all we're thinking is that it has the symbol and it has a number at the bottom, which we're going to call A, has a number at the top, which we'll call B. It's going to have some function in here. So let's just call this f of x. And what am I missing from my notation here? We're missing the dx. Okay. Now that's a really good question, Eric, about why is it a minus sign? Okay. So this minus sign right here, it's so the short answer is that is the process. Okay, that is the process with which we do this. So if I were to write out my definite integral, I would say this is capital F of B minus capital F of A. Okay, so it is part of the process. However, if we sort of think about what we're trying to find, gosh, what's the best way to describe this? We're trying to find like if we just plugged in 4, then that would be like all the area all the way up to here. Okay, so like all of the area that came before all the way up to 4. And if we just have 2, that means it's like all the area up until 2. So if I want to find the area between them, I'm going to subtract them. This is sort of similar to like, if you have like a rectangle and then we want to find the area between like the 2 rectangles, we would find like the area of the big one and we subtract the area of the small one. It's kind of like that idea here, Eric. But we'll talk a little bit more about why it's a minus, okay? All right, so this right here is probably a good definition to make sure you have down. It is sort of like a general form of what it means to be a definite integral. But we're gonna practice a little bit with just the area part, and then we're gonna come back and practice a little bit with the definite integral part. Okay, so let's first focus on some area just to brush up on our area formulas again, and then let's come back and let's try our hand at the algebraic way of doing this one more time. All right, so we've got this diagram. Okay, now all of these questions here are what we call definite integrals because they have a number at the bottom and a number at the top, right? These look really gross though. Like I don't want to do these using algebra, okay? So we are gonna instead use the fact that we know a lot about area. We're gonna use area to solve these problems, okay? So let's begin. Let's take a look at our diagram a little bit more closely, okay? So we've got a few different shapes here. What might be some good area formulas for me to write down before we start working on them? Area of a circle. Okay, so area of a whole circle is, and we need to know about a triangle. Yes, I agree. All right, what are those formulas, folks? What's the area of a triangle? What's the area of a circle? 1/2 base times height, area of a circle. Not 2 pi r, but yes, Christina, pi r squared. Yep, that's gonna be a sad mistake to make, okay? Don't make that mistake. But I noticed that I don't have a whole circle here. So how might I write for only half a circle? Divide by 2, good. So it's not that it's a different formula, but we're learning a different way to write it so that it's more useful in this particular question, okay? All right, so we've got these formulas here. Let's go ahead and take a look at these questions. So for part A, it says find the integral from 0 to 2 of 1 minus the absolute value of x minus 1 and I'm going from 0 to 2. So what shape does that correspond to? It's the triangle, good. And if we were to sort of outline that on our diagram, we've got this triangle right here is the area from 0 to 2, okay? So let's apply our formula. We can say that it is 1/2 base times height. And we plug in 1/2. Our base in this case is 2 units long and our height is 1 unit tall. And let's not bother with the multiplication. Let's reduce before we do that. And we end up with an 1 as our answer. Okay. Not so bad, right? Let's try C. I know that's out of order, but let's try C. All right, so do that one on your own real quick. How might you apply what we did in A to answer part C? All right. Well, and looking at C, I hope we notice that we are going from 6 to 12. And actually, that should be the other way around. My apologies. 12 6. Okay. I hope we are able to recognize here that this, again, is a triangle. Wow, triangle. Okay. And so we reach back into our toolkit of triangle area formulas, 1/2 base times height. And let's see, what is the base of this triangle and what is the height of this triangle? Who's got values for that? 6, I agree, is the base, and 3 is the height. Perfect. Okay, so 6 times 3, and I'm going to go ahead and reduce that to a 3, and we get an area of 9. Okay. So we found, we found the area of the first triangle and of the second triangle. Okay. Now we do need a different formula for this second piece, part B, because this one from 2 to 6 is not a triangle, but it is a semicircle, right? So let's go ahead and identify that, and then we'll figure out what numbers to plug in. This whole equation is a semicircle. And so I'm going to have pi r squared over 2, and our radius in this case should be 2, right? So we'll get pi times 2 squared over 2, which should give us 2 pi as the area. So, well, sorry, so many zooming in and out, but how are we doing with A, B, and C? Are we okay with A, B, and C? Good. Okay. Now, I hope it's clear here that we have area formulas. And so if we can use the area formula, it is actually a fairly straightforward problem because we're looking at like things like the radius or the base or the height. Okay. Now, there is one thing that is different about D. Okay. So in looking at D, here are a few things. We are starting at 6. And we are going from 6 to 4. Okay. So knowing that we're starting at 6 and we're going to 4, let's actually draw that on our graph. Okay. So if I'm starting at 6, I know that I'm starting here. And when I'm ending at 4, I'm ending here. Okay. So 2 things here. What is the shape? All right, let's deal with that one first. What is the shape that I've now sectioned off? Yeah, it's just going to be a quarter circle, right? Because it's half of a half circle. Well, we don't have a formula for that, but as long as we know our area of a circle, we can just divide that by 4 instead of 2, and then find this area. Okay. So let's go back to our question. And instead of saying pi r squared over 2, we're going to say pi r squared over 4. And we're going to get pi times 2 squared over 4. And we know that that's pi. Okay. All right. So we've got these 4 questions here. Okay. And our answers. Does anyone have any questions before we move on? Okay, so I see one question, which is, shouldn't the 4 be on the bottom of the integral? Actually, in this case, it is intentionally not 4 on the bottom. Okay, so sometimes, most of the time, we have the smaller number on the bottom, but sometimes we have the bigger number on the bottom. Okay, that's one question. Are there any other questions that are coming up? And yes, Isaac, that's a great question. It does actually matter, right? That's one of the things I'd like to talk about before we leave this page. It does make a difference which number's on the bottom and which number's on the top, okay? Any other questions or wonderings based off of things you've noticed? Okay, well, I'll share one wondering that I have. If I were looking at this graph for the first time, and maybe let's get rid of these for right now. And I might say that, hey, this area, we said this area is 1, right? But I'm like, this is on top of the x-axis. I think that's a positive 1. But if that's a positive 1, and this is a positive 9, is this a positive 2 pi? That would be a question I have. How would we know that it's negative? I mean, I agree with you. I think there needs to be some sort of distinction here, that like if it's above the x-axis and we're saying that's positive, maybe we need to consider what happens if it's below the x-axis, okay? And so I would agree in this case, we actually probably want to put a negative sign in front of that, okay? So in just looking at this picture, and I'm going to say, understanding how we read English, because not all languages are read this way, but when we read English, we go from left to right, correct? We go from left to right. And a lot of times when we're reading math, we do the same thing. And so when we're reading from left to right, everything is as it seems. Above the x-axis, positive. Below the x-axis, negative. Okay. However, if we go in the opposite direction, what happens is we end up changing our perspective on everything. And things that were positive in one direction become negative when we approach it in the other direction. Okay. So what that means is these blue numbers here are entirely accurate as long as we're reading this way. Okay. So as long as we read from left to right, then the areas are 1, -9, and or 1, 9, and -2 pi. However, if I read in the opposite direction, from right to left, what should I change that positive 9 to? Yeah, so let's put a pink number here that this one is going to be -9 if we go in that direction. What does that make our -2 pi? It becomes a positive 2 pi. And what about that 1? -1. Oh, I did not leave enough space. We'll just draw a little arrow, -1. Okay. So when we're going in one direction, in the one that we traditionally go in, that left to right, everything is as it seems. Above the x-axis positive, below the x-axis negative. However, when we go backwards, then we also approach things in terms of a different perspective. Now, what was positive is negative, and what was negative is positive. Okay. So knowing that, I'm going to change my answer for part B. Instead of saying 2 pi, we want to say -2 pi. Okay. Now you tell me, what sign should part D have if I'm starting at 6 and going to 4? Starting at 6. All right, so if I'm starting at 6 and going to 4, is that the blue direction or the pink direction? Yeah, it's that pink direction, right? So that's not going to be negative because I'm going in the opposite direction, but our answer here actually should be a positive pi. Okay. But when you go back and study later, you might need to spend a little bit more time thinking about B and D and how come one is negative and how come one is positive. Okay. So when I wrote question C, if I kept it the way it originally said, the integral from 12 to 6 of 3 minus x minus 9 dx, then we would have said our answer was -9 because we're reading in the opposite direction. Okay. I know that can be a little messy in the brain. There are questions on the quiz like this. So I would encourage you to kind of practice that thinking, like, how do I know when things are positive or negative? Okay. Great question, Ethan. We're actually going to talk about that probably after break. So we can only determine our final answer's positivity or negativity by looking at the graph, right? If problem like this on the quiz. Yeah, so you might have a picture, but I might also just tell you what areas are, and knowing the direction, if we flip the direction, then it would be a different sign. Does that make sense? But that is something that I do still kind of do when I'm like when I'm finding areas and stuff. I'll maybe compare it to the graph of the function so that I can tell, like, oh, did I get a negative area? Okay, that's fine because it's like all underneath the x-axis. So that is actually a good way to check your work. Okay. All right. So before we go on break, I'd like to take a look at this question here, example 3. Okay. And so in example 3, you'll notice that there is no diagram. And so this is, in particular, if there's no diagram, then someone is asking you to use definite integrals to find this area. Okay, so we'll use the definite integrals, and then at the end, we'll draw a picture of what it looks like. Okay. And yes, Eric, I think that's a really good point. Okay, so no graph. We're going to use definite integrals. And I know it's definite because I have a number on the bottom and a number on the top. So 1 and 0. And my function 1 minus x, that quantity squared. And I know I'm looking for area because I have the integral symbol and that dx. Okay. So here's what we're going to do first. if we were taking a derivative of this pink part or the red part, 1 minus x, that quantity squared, okay, what rule would we use in derivatives? Right? Like if I were taking that derivative, I would 100% want to use chain rule, right? Now, we don't know chain rule for integrals yet, but that is the big rule we will learn next week or the week after, okay? So we don't know it yet. And since we don't know it yet, exactly, we're gonna FOIL so that we can turn it into a problem we know, okay? So the integral from 0 to 1, and we have, let's see, 1 minus x, 1 minus x. So I get 1 minus 2x plus x squared. Okay. So we FOIL because we don't know how to do chain rule with integrals yet. Okay. So we FOILed. Now let's take our antiderivative. Okay. So I'm going to take the antiderivative of each part. Then I'm going to put those brackets around them again. I'm going to draw the little line at the corner with the 0 to 1. Okay. So 1 will be 1 times x to the 0 plus 1 over 0 plus 1 minus 2 times x to the 1 plus 1 over 1 plus 1 plus x to the 2 plus 1 over 2 plus 1. And I don't want a plus c because I have the numbers. Draw a little line, put the 1 at the top, put a 0 at the bottom. 0 and 0 and 1 and 1. Okay. Now, again, this looks really gross, so let's simplify before we start plugging in any numbers. So x minus, let's see, 2x squared over 2 is just x squared plus x cubed over 3. And we're going to plug in 1 and 0. And after we plug in 1 and we plug in 0, we are going to subtract them. All right, let's plug in our numbers. Let's see what we get. 1 minus 1 squared plus 1 cubed over 3 minus 0 minus 0 squared plus 0 cubed over 3. And so all of these are from plugging in the bottom number, and all of these come from plugging in the top number. And let's see, we get 1 minus 1 plus 1/3 minus 0. And so we get 1/3 as our area. Okay. So having seen that procedure a second time, how do we feel about that? Better than the first time? Worse than the first time? Questions? Okay. Now, if more examples helps, all right, we don't always go over a ton of examples. In fact, I sort of choose carefully how many examples we're going to do in class. This is part of the reason why this week's math and writing assignment is about finding more examples, okay? And so before we take our break, I'm going to go ahead and just graph the function that we're looking at. So 1 minus x, that quantity squared, okay? And what we get is a parabola, okay? So the graph of this looks like now, what part of the graph are we interested in? Like the whole graph? Part of the graph? What are we interested in for this particular question? From 0 to 1. Perfect, perfect. So if I'm thinking about graphing on Desmos, it's easy to kind of stretch and shrink on Desmos, but if you were using a graphing calculator, you would want to make sure to bring that domain in to like 0 to 1, okay? But when you graph this, you end up seeing that you have a parabola like this. It's much prettier than the one I'm drawing right now, but we have some parabola. And we're going to start at 0, and we're going to stop at 1. And it turns out that the area of this shape, which is almost like a triangle, but not quite. All right, so it's kind of like a curvy triangle. If I had drawn it better, the area of that shaded region is 1/3. And so, as Richard was suggesting earlier, maybe knowing connections between the graph and the answer will help you make sure that your answer is correct. In other words, I can look at my graph and say, I better get a positive number out. Okay. And the only reason I say that is because sign mistakes happen. There are so many places to make sign mistakes, right? And so especially if we plug in, like if we start plugging in like negative numbers, we might see how there would be a lot of sign mistakes possibly happening. And so in order to double check ourselves, we want to make sure that our picture matches the idea of the number there, okay? All right, so this seems to be a good time for a break. So it is 10:34 right now. Let's be back at 10:45 a.m. All right, so I'll see you folks back here in about 10 minutes. If you have not sent your self-care sentence to me yet, please do that through the chat, and I will see you folks back here in about 10 minutes. All right. So net area versus total area, okay? We're gonna do one example on this. I know that it's not that many, but I think that there's a lot of value in this one particular problem. And I think that concept will hit upon one of the questions that was brought up earlier about like, what if maybe the area, like, can the area be 0 at some time, okay? So let's take a look at this question, all right? This says, find the net area and total area for this integral, okay? Now we know that this is a definite integral because we have our number at the bottom. We have our number at the top. And if we didn't have those numbers, we might just say antiderivative, or we would say indefinite integral. We know that we have this function, x minus 2, and we've got our integral notation, which is paired with that dx, okay? And so luckily, Desmos has created a graph for us, so we do not need to worry about graphing. But the net area is actually another example, very similar to what we did just now in terms of finding the shapes and using antiderivatives to find an exact area. We know we're going to start with this part at x equals 0. And we're going to go all the way until we get to x equals 6. Okay. And so if we were to shade this area in, we might notice that we have this part down here, right? And then separately, we have this part here. Now, when we draw these, it's really important that the area that we are shading in is the area between the curve and the x-axis, okay? Sometimes people are like, oh, here's my curve, so I'm just gonna make like a big old triangle or whatever shape it happens to be. But what we're looking for is the area between the whatever the function is and the x-axis. That's why we have those two yellow triangles instead of like that big triangle that we would have had. Okay. Now let's use a little geometry to help us out here. And so if we go ahead and find the area of this big triangle, we would get, let's see, 1/2 times 4 times 4 is 8. Is that correct? We're getting an area of 8 for this big yellow triangle. Yes, okay. And would we call that a positive 8 or a negative 8? Yeah, we're going to call that a positive 8, right? Because we're reading in the typical direction for English, which is from left to right. So everything is as it seems, nothing to worry about. And if we find the area of that little yellow triangle, we might notice there's 1/2 times 2 times 2, which will give us 2. However, since this one is below the x-axis, we won't call that a negative 2, okay? And so if we find the net area, okay, so net area would just be -2 plus 8. Like we just add them together, okay? And we get 6. Does that part make sense? We are just sort of like starting from the green line, we go all the way to the blue line, and then we get -2 plus 8. Okay. Now, the total area, okay? The total area is a little bit different. All right, so net is not like the total, all right? It is in the sense that we're still looking at area, okay? However, net area is sometimes referred to as signed area, meaning that if something is below the x-axis and we're reading from left to right, then it's going to be negative. And if something is above the x-axis and we're reading in the same direction, that's going to be positive. Okay, so signed area, meaning there can be positive and negative area. Okay, there can be positive and negative area. And yes, exactly. Okay, there we go. So total area, we're still going to start and stop in the same place because our integral says so. We start at 0, we go all the way to 6. But this time, we're going to say that this area is still positive 8. And this area is still -2. However, when we add them together, we're going to take the absolute value of each piece and then add them together. So -2 absolute value plus 8 absolute value will give us 2 plus 8 or 10. Okay. There we go. Okay. So the net area is sometimes referred to as signed area, meaning that if there's more negative than positive, the overall net area will be negative. If there's more positive than negative, the overall net area will be positive. However, with total area, we're always going to get a positive number. Okay, the total area just means like how much area is there. I don't care if it's positive or negative. I just care that it's there, okay, or that it exists. Exactly. All right, so with total area, maybe the note we want to make to ourselves is that this is the absolute value of each piece of area. Okay. I think the parking spots analogy is a great one. And if you're finding the total area, it depends. If you label this as a +2, that's not quite correct, right? That area is still negative, but it's only the phrase total that says, hey, put these absolute value pieces there. Okay. So I guess maybe a different question is like, if you have the same picture, but you label them differently, maybe you've changed the meaning of that picture, right? So we sort of change that in our equation rather than in our diagram. All right, so I know this is only one example, but in terms of thinking about the concept here, basically when we have signs, we're thinking net area. Everything is positive, then we're thinking total area. Okay. And so that's a concept that if you're feeling a little stuck on, again, this week's math and writing assignment is to find some resources, do some other kinds of practice problems from those resources. And so maybe you look up something that talks to you about net area versus total area. Okay. All right. So let's go ahead and move on to this section. Okay. So this section, is called Properties of Definite Integrals. And I know that we don't always love working in groups, or sometimes it can be hard if we're all feeling stuck. But I'd like us to do a little bit of work in breakout rooms, and let me kind of explain what that's going to look like. So we have this list of properties, okay? This list of properties. All right. And sure, you can memorize them, right? What happens when you forget them though? And also knowing that Judy likes to ask questions about sort of the concepts behind things, I think it would probably be valuable to think about where these concepts come from and how they might look in a picture, okay? And so we're gonna do one of these together. We're gonna I'll model what it is that I want you to be doing in your breakout rooms, okay? And then you're gonna go into breakout rooms and work on a few of these together. I know that not everyone has a tablet, which is never to be expected, right? It's certainly a luxury and a privilege to have such things. But if you have one, I would ask that maybe you volunteer to share your screen for your group, just because I think that that would be of huge benefit to everyone in your group if you're looking at the same diagrams, okay? Additionally, if no one in your group has a tablet, you can still open up a whiteboard, I believe, in Zoom. Okay. It's not as nice because you are using a mouse or a touchpad to sort of draw things, but it is doable. So that is sort of an alternative, but I would ask that you are all contributing to these conversations, and more than anything, my curiosity is around like, how do we make sense of things that are newer for us, okay? And so what we're going to do right now, again, I'm going to sort of model what it is that I hope happens in the groups, is I'm going to go ahead and do the last one, okay? So we're going to go ahead and take a look at, let me go ahead and grab this particular rule, okay? And what we're going to do is we're going to draw a picture that goes with said rule, so that we can kind of think about what this rule means rather than just sort of memorizing that rule. Okay. So we've got something that says integration with horizontal translations, lots of big words. And symbols. We've got a definite integral. So the integral from a to b of f of x dx is equal to, and did I not grab the whole rule? Oh, I sure didn't. That should say f of x dx on the end. So sorry about that. Okay. So the hard part about this activity, and I know this sending you in, that's why we're doing sort of an example together, is that there are no numbers, okay? Now, this is sort of similar in flavor to the idea of that discussion question I had you look at last week, where I gave you a question that didn't have numbers really, but I wanted you to address the concept, okay? So that idea of being able to work with the idea of numbers rather than an actual number is definitely a place that I think we can all kind of grow a little bit in, okay? So when you get into your groups, here's sort of what I'm thinking, all right? You're going to take one side of the equation. And so for this one, let me just grab this part. And I'm going to draw a diagram that represents that part. Okay. I don't know what f of x is, and it doesn't actually matter. And I think that's sort of the weird thing. It doesn't matter what f of x. So I'm going to just draw f of x. And then, like before, I'm going to have a bottom number that I'm going to mark off on my x-axis and a top number that I will also mark off on the x-axis. And so let's go ahead and draw, you know, all my functions look the same. All right, I've got some function here, and I don't know where A is, I don't know where B is, but I'm going to draw, I know that they're x values, so I'm going to draw them on the x-axis, okay? So here is like my A, and maybe here is like my B, okay? And if I were to kind of follow in line with what we've been doing, I know that that integral represents this area right here. Okay. Any questions so far? Are we okay with this diagram representing this? You can give me a quick thumbs up or a yes or a no. That's also a valid answer. one yes. I was hoping for more responses, even if they're no. All right. And remember, if you do not want to say, no, I don't get this to the entire room, you can simply whisper it through a direct message and say, hey, I don't really understand this, okay? It's actually one of the benefits of being online is that you can secretly tell me something and not have everyone hear. Okay, so now let's try drawing the right-hand side, okay? We already used that color. Let's draw this side, okay? And so I'm gonna go ahead and take this and let's see. If I have A plus C, this A plus C is my bottom bound, and this B plus C is my top bound, okay? So all I've gotten is a plus C on both regions, both the starting point and the ending point. So what I'm really doing, and this phrase here gives us a hint, that we're basically taking the picture we have and we're sort of sliding it over C units. Okay, C could be 1, C could be 2, C could be 3. It doesn't really matter, but if I'm taking this whole equation and I'm shifting it to the right, all right, let's say, or the left, then we have our same graph, except we have different starting points, okay? Meaning that we have our graph. We'll try and duplicate this as best we can, but now we are starting at our A plus C, and we're ending at our B plus C. Okay. And one thing we might notice is that the area, because we're sliding the entire graph, and oh shoot, I forgot a really important part here. X plus C, all right? So if we move the entire function in one direction, it's almost like, yeah, sorry, it's almost like we just picked up the whole picture and we just slid it over. And so the area is still going to be exactly the same. Okay. And we can see that our diagram here matches this part of the equation. But when we look at the two diagrams, we can tell that those areas are equal to each other. Okay. Because we're taking f of x plus c, which means we take our whole function and we just move it over. So the shape is exactly the same because we're moving the whole function over. Yes, 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 exactly. Kind of like when we were doing all of those graph transformations, if you were in Math116 and we were like, oh, f of x equals x squared, and then what does this do? Okay. And this 3 just moves that parabola to the right 3. Yeah. Okay. So this is one way to show things. All right. However, as Ethan is suggesting, maybe you folks draw the same diagram or the diagrams on the same x-axis. That could be a way that your group chooses to approach things. Okay. So does that kind of make sense what I'm asking you to do in your groups? Maybe if we could just have someone summarize and put that in the chat, like, what are you going to be doing when we move to breakout rooms very shortly? Nope, you're totally fine. I agree. I think that this one, if I had thought about it more in advance, I would have drawn them on the same one. Yeah. Okay. That's fine. That's fine. All right. So what you are going to do in your groups is the following. Okay. So this was our example. All right. So if you want to take a screenshot of this right now so that you have something to look at in your groups, come back to and refer back to, that would be fine. I'll give you like a little bit of time to do that. And then I'm going to scroll back down to the list of formulas that you're actually going to be working with. Okay. So in your groups, what you're going to be doing, and we will have bigger groups just because I think, again, with the technology piece, my hope is that one person in the group might have like a tablet or something that'll make it easier to share. But again, you can also just go ahead and do a whiteboard on Zoom. That's also fine. All right. But one thing you'll notice that we have here is we have 4 rules that we didn't get a chance to draw yet. Okay, so these 4 rules are what you're going to be working on drawing in your groups. Okay, now when I put you in breakout rooms, each room will have a number. All right, so I'm going to put a 1 next to the property that I want group 1 to do. I'm going to put a 2 next to the property I want group 2 to do. I'm going to put a 3 next to the property that group 3 is going to do. I'm going to put a 4 next to the property I want group 4 to do. Does that make sense? So when like think you might want to take a screenshot after I write the numbers as well, so that when you get into your groups, you'll know which numbers or which ones you're supposed to be focusing on. Okay. So here we go. If you were in group 1, I would like you to take a look at this one and this one, right? If you are in group 2, I would like you to take a look at this one and this one. Okay. If you get to your breakout room and you were in breakout room number 3, you're going to be looking at this one and this one. And breakout room 4 will have those. Okay. So take a quick screenshot if you need, so you have the rules too, and you know which numbers your group is going to be responsible for. All right. Are there any questions before we go into our breakout rooms? Okay. Also, as a heads up, I will be asking folks to draw things when you come back. So either you have that on a tablet if everybody, or if there's at least one person in the room who has a tablet, or as you're drawing on your Zoom whiteboard, maybe take some screenshots. You could share those with me and then we can take a look at those. Okay. So there is very much a deliverable when you return beyond how did it go? Okay. Before we go, I'm going to stop the recording or pause it.
Was if we had a constant, then when you take the area of the 2 different integrals and add them together, it should just equal the same area from B to A. So here we just said our constant was like 2, and we just kind of assumed some values, right? So we said if the area between 2 and A was 5 and the area between B and C was 15, when you add them to, except it's negative because B is over C. When you add them together, it's -10, which should just be the area between A and B, or B and A.
Okay, why don't you keep that on the screen for a moment? The other group, which I think it was group 3, how does that compare to what you had? And if I could get someone from group 3, you don't have to unmute if you're uncomfortable speaking, but if you could maybe type into the chat or unmute, your choice, how that compares to what you had, that would be wonderful. And folks in group 3, if you were in a room with ISIS, you were in group 3. So I don't know if people knew what room they were in, but if you were in that room, how does this compare to what you had for interval addition?
Okay, I guess I'll go. We pretty much had the same idea. What we were caught up looking on is we realized that some of them were going from left to right and some of them were going from right to left. That where we found the area. And but the whole addition, how the two values added up to the other one, was pretty much our main takeaway.
Okay. Well, I agree with mostly with what's here, except that although we would like the letters to be alphabetical, right? That maybe that's not always the case, and that we need to be thoughtful about what the bounds represent. So in this particular question, the first interval goes from A to C. And so what would that imply about your, if we assume we're going from left to right and the bottom number is A and the top number is C, how would that change?
Oh, it's
How would that change?
So you would need
so we would have to. So we're
you would need
assuming
to
we're
be on the
going from
right
left
side
to
of it.
right.
Yeah. Let's put the A first.
We screwed that up too.
Yeah. Okay, so let's put the A and then the C. Okay. I think this is where those of us who maybe are like, okay, but it goes A, B, C, it just is a little uncomfortable because the C is in between the A and the B, right?
We
But
went
now I think we can read all the intervals from left to right.
Yeah, so that would just be, I don't know. I'm kind of confused what you mean, actually.
I think I see it now. This makes it a lot easier. It's just the two little sections. I wish I could point them out or equal to the whole thing. Right?
Yeah, so let's see. If we say that the area of this first region from A to C is like a star, and then we
Yeah.
say the area from C to B is the heart, then the area from A all the way to B would be the star plus the heart,
Yeah.
or like
That
5.
Right. So I understood that, but what doesn't make sense to me is that since the C is over the A, why is it going from left to right?
We start with the bottom number. So the bottom.
Okay. That's
Yeah, there we
that's
go.
where I went wrong. Okay, my bad.
Cool. Yeah. So folks who were in rooms 2 and 4, you didn't have a chance to look at this. What are your thoughts about this particular property? Are there any questions kind of coming up right now or clarifications you would like to ask for?
So if they didn't line up like that, if one was going from right to left, it should still work the same way, or no?
So I think if you look at your the intervals here, what makes them actually very special is that the top number, the C over here, is the same as the bottom number in the second integral. So one way to think about it might be that if the top number in the first integral is equal to the bottom number in the second integral, What it means is that like they meet, the two pieces that you're trying to find the area of meet at this point.
Right.
Yeah.
Okay.
So if those numbers, like if it's a C on the top of one and a D on the top of the, or a D on the bottom of the other though, I would say that this property would not hold true.
Okay.
Okay. Okay. Cool. Thank you for sharing that screen. I'm going to go ahead and clear my drawings. We will also summarize these as a group. Okay, so I know we'll get a chance to see them again. But Eric, you can go ahead and stop sharing your screen. And I wonder if anyone from group 2 or 4 would like to take a look at sharing the backwards integration one that you were looking for.
I can share that. And group, just quick updates on what we did. I kind of changed, like improved the Desmos thing we did. So we didn't have a tablet, so we quickly worked something out on Desmos. And so here we have an f of x, which is the graph you're seeing. And we don't actually need the graph. It doesn't quite matter necessarily. But what you're able to see is if we have an integral from any b to a, and then we have the same integral here of f of x, but this time it's a to b. No matter what the bound is, you're always going to have the they're going to be opposite signs. So if it's negative 2.5 to 5.2 and 5.2 to negative 2.5, it's going to be the same area, just different sign.
Why is that though? Like we know it's true, but why is it true?
Because whether you're going left to right or right to left, the area under the interval that you're taking. So let's say I was to say like -3 to like 1. And I'm just going to quickly, oh, that didn't work. -1 to 0. So it's 0.75 and -0.75. And I would, if I were to annotate on my screen, that area under the curve. So A to B, so A is right here. And then B is going to be right here. And then the area I'm looking at is all of this. That was kind of sloppy, but whether I'm taking that area from 0 to 3 or -3 or -3 to 0, it's still going to be the exact same amount of area. So like, I guess in a sense, the total area is going to be the same backwards and forward. But since, you know, the x-axis is going towards bigger numbers when we go this way, it's gonna, this is gonna be a negative area and this is gonna be a negative area. And this is gonna be a positive area. But because the x-axis is going from positive to negative, if we go the other way, which is right to left, then suddenly 0 to 1 becomes the positive because we're going backwards. And so the sign of the total area is switched from positive to negative.
All right. So this really is just a generalization of what we were talking about in, which example was that? Example 2D, where we had that quarter circle and we were going backwards. And so it changed the sign of that region. All right.
Yeah.
So yeah, if you want to think about it that way, it is very similar to what we did in example 2 for that property. Okay. Well, thank you for that. Let's see. All right. Integral of the sum or difference. So which group? Either 2 or 3.
Professor, I have a question about that one.
Okay.
Was the second f of x, like it has a little integral sign, f of x dx plus or minus and the integral thing again.
That's
G
g of x.
Yeah, sorry, I kind of forget how to say it. So is that supposed to be a g of x?
Yes. Yeah.
Okay, thank you.
All right, did either group 2 or 3 get to this one or have some ideas about what that might look like?
Group 3 did. We didn't really come up with an actual like answer to it, but we did throw ideas out.
Okay, what ideas do you have?
Let's see. And we noticed that f of x was the same, and that we started with a and we ended with b for both of them. We also noticed that these signs right here stayed plus or minus, so like there wasn't flopping on each side. And we drew up two graphs. Since we saw the f of x here, we drew an f of x and then a g of x, and we had the idea that maybe somehow they were connected, that they crossed somewhere, and that maybe we were describing area somewhere in here.
Okay, yeah, so that was a great catch on the typo by Thea, so the first blue f of x is supposed to be f of x. The second blue one you have is actually supposed to be a g of x. And that might have actually made things much easier for you, okay? But you're right though, I think you've got the great concept here, which is that if I have the region from, oh my gosh, where is it? Oh. If I have the region from A to B and I want to find like each piece of it. So if I find like sort of this area down here, I don't know if you want to shade that area underneath like your f of x curve.
I can't see what you may or may not be doing on the screen, so I'm just gonna take my best guess of what you're saying.
All right, so you see where your A and your B are?
Yeah.
And you see how you have the f of x function? Can you shade the region between that curve and the x-axis?
This one.
Yes. Okay, so that would represent that first integral there. Now, if you said, I want to shade the region from A to B between g of x and the x-axis, what would that look like?
This right here.
Okay, so we have that blue area and sort of like that gray tan area. And so if we wanted to find out if I added the functions together, what would that area be? It would just be the blue area plus that gray area. All right, so
awesome.
we're looking at that screen, right? Yeah, and so that way we can, if we know that we want to add the functions like on the right-hand side of that equation, we can just say, I know this part and I know that other part, so I'm going to add them together. Okay, so thank you for sharing that. Cool. Now, did any group get to the scalar multiple one? I know that was question, or the last one there, that scalar multiple. I know one group said they did not get to it. Did the other group happen to get to that one? Yeah, I think both groups had actually said no. Okay, so let me share my screen. Okay, here we go. So for this last one, if we were to grab the scalar multiple one, this definitely has a bunch of typos. No one has ever told me before. Okay. This will be a B up here. This is supposed to be an A, and this is a B. Okay, so we might notice here that our bounds are the same. On the bottom, we have A, and on the top, we have B. And K stands for a constant, okay? And so K would be like a number, just a number, all right? And so if we imagine that we have just f of x, okay, so let's say that we have some function f of x, and I want to start at A, and I want to finish over here at B, and I have this area, and let's maybe say this has an area of +5, okay? Now, this K here, pick a different color, this K means that I would take my area and I would multiply it by K. So if K were 2, what would that new area be? So if I have this as an area of 5, and now I'm telling you that you're multiplying it by 2, yeah, you're going to get an area of 10. And so if we think about 2 times a function, all right, so 2 times a function, this 2 is the same as a vertical stretch, okay? And so if we think about what that might look like, a vertical stretch will just take my function and make it twice as tall. Okay, so it makes every y value, this is 2f of x. It makes it twice as tall. Turns out, if you keep the bounds the same, now there's going to be twice as much area here, and it will be 2 times 5 or 10. Okay, so we use this rule a lot. We've used it a lot and not even talked about it. I was like, oh, if there's a constant, just pull that out to the front. Well, it'll save you some work later on. And all of that is true, but when we think about this particular property, we're tying it back to graph transformations and what that does and how that changes the area underneath that curve. Okay. So I know this was a departure from our regular sort of, going through the properties or whatever it is that we're learning. How are we feeling about these 4 properties, right? And you can send me a message and say 1, they all make sense, 0, I'm not really sure, and a -1 if you're like, oh, this is really tough. So this picture represents both of them. I thought I would try the suggestion of putting them on the same graph so that we could kind of see it. But the 10 represents the area between the pink curve and the x-axis, whereas the 5 represents the area from the black curve to the x-axis. Does that clarify that? All right, well, let's try a couple examples and kind of see what it's like to apply these, okay? Seems right now we're trending closer to -1 than +1, and I would like that to change if possible, okay? So example 5 will be the last one we do today during class. And so let's think about what this means, all right? So this is a very typical kind of question. It is very abstract in the sense that you have numbers for the bounds, like -1, 1, 4. However, you do not have any pictures. And that's why I wanted us to spend some time drawing pictures, or at least watching other people and discussing how those pictures might be drawn. Okay, so we can certainly memorize the properties, but in terms of like justifying why these things are true, I think the diagrams can really help with that explanation. Okay, so based off of the properties, what are our thoughts for this first question, part A right here? All right, I've got the integral from 4 to 1 of f of x dx. I see one answer as a 2 question mark. Okay, well, maybe we should actually start by looking at the information we have, right? So many integrals, but that is the life in the day, or that is a day in the life of a calculus student. We've got these bounds, right? So for f of x, I know from -1 to 1 has an area of 5. I know from 1 to 4 has an area of -2. And for a different function, h of x, from -1 to 1, I actually have 7. Okay. All right. So for part A, I have 2 guesses and they both say +2. Which rule or property did those individuals use? Exactly. We might notice, hey, we have some information about what happens from 1 to 4, and this one is just asking us to use the other direction, backwards integration. All right, and I agree that this equals a +2. All right, but if we were to try and draw a diagram for that, we might even be able to strip it down a little bit more and say, here is our x-axis, and I have f of x from 1 to 4. And I know, actually, that's not the right picture, right? I would want to make sure this is drawn underneath. So I've got some function, f of x, and from 1 to, oh my gosh, 4, I know that that area is -2. Actually, let's go, this is -2 when we read it in this direction. And so if we're reading it in the other direction, then we would say that that has an area of +2. Okay. I know this is sort of a simple case, but does that make sense, like how we could use a diagram to help us explain why we have the areas we have? I'll take that as a no, but let's try another example to make sure that we can maybe start to say yes by the end of class. All right, so what about part B? What property do you think would apply for part B, given the information that we have? All right, we have 1 vote for interval addition. Any other votes? Interval addition. Yeah. Now, what makes us say interval addition? I mean, we're right, but what about the given information tells us we're going to use interval addition? the C will be between -1 and 4. I love it. I love it. So if we think about our bounds, we have -1 to 4 or to 1. Remember how I said that top bound better be the bottom bound somewhere else? And then that's the only time we can add them together. That's what we're talking about right here. Okay. So 4 is our top bound here and -1 is the bottom bound. So we can take the two pieces of information that we have for f of x and apply the rule and just know that we're almost going backwards, okay? So we're saying integral of -1 to 4 of f of x dx is equal to the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. Okay, so I'm just writing that property down, but in a backwards order, because now I can substitute values that I have. So instead of -1 f of x dx, I will put a 5. And instead of the integral from 1 to 4, I will put -2. And so that means that the entire interval has an area of +3. Okay. Does that help clarify things a little bit in terms of how we use these properties? Okay. So let's take a look at C. All right, we're going to set up C and D, I hope, in the time that we have left. So for C, what rule or rules seem like they might be helpful? Okay. So we've got a scalar multiplication and interval addition, and the addition, yeah. So sometimes you're going to need more than one property, just like sometimes we need more than one rule for derivatives, okay? So let's go ahead and write down that we're going to be using the scalar multiple and the integral of some difference. Some difference and scalar multiple. Right? And so if we were to apply those, we could break this up into two different integrals. So this would be 1 plus the other one. So this would be the sum difference rule. And then I could apply the scalar multiple and do something like this. Okay. So that's applying the rules. I'll leave it to you to fill in the numbers, okay? But making sure that you choose appropriately, like, is this the F1 or the H1, okay? All right, I would like to finish off with number D over here, from 0 to 1 of f of x dx. And looking at the list of properties, which one or ones do you think fits best for D? Any properties jumping out at folks for D? All right. Well, if there are no ideas, then I would encourage you to look in your textbook, see what you can read up about this. This is actually not the horizontal translation one, okay? So I think that's a good guess. It's actually not the interval addition either, also a good guess. It's not backwards integration. Now we're just reading off the list. Yes, no. Okay. All right. Well, on that note, good luck figuring it out. But I will be around for office hours on Friday morning if you would like. Yeah, it is tough. It's a little bit, sometimes we need a little bit of tough love. Okay.